Hello students, in this lecture we are going to discuss, we're going to do some problems on statistical mechanics. The first problem is calculate the occupation probability at 2 kT units of energy above the Fermi energy. So the occupation probability Fe is nothing but number of states or of particles per unit state for according to Fermi Dirac is e to the power E minus EF by kT plus 1. So according to the problem, E minus EF or is equal to 2 kT. So that makes occupation probability Fe is equal to 1 by e to the power 2 plus 1, and the value turns out to be 0.119. The second problem is to find the Fermi velocity of the electron in a metal the Fermi velocity of the electron in a metal is given as 0.7 into 10 to the power 6 meter per second. We need to find out the Fermi temperature. It's the F. Now Fermi energy EF, write in terms of Fermi velocity, it is half mvf square, and the value of Vf has already been given here. So you can write this as 1 by 2 into mass of electron, that is 9.1 into 10 to the power minus 31 kgs into whatever we have been given, that is 0.7 into 10 to the power 6 meter per second. So this turns out to be equal to 2.4 into 10 to the power minus 19 joules. And so Fermi temperature, you know that EF is equal to KTF. So TF will be equal to EF by K, the Boltzmann constant. So EF we know as equal to 2.4 into 10 to the power minus 19 joules, and the value of K is 1.38 into 10 to the power minus 23 joules per Kelvin. So ultimately we get the value of TF as equal to 1.73 into 10 to the power 4 Kelvin. Now, the next question is not numerical. Uh, it has been asked that out of the three gases, that is, out of we have three different statistics in statistical mechanics. One is the classical one, that is your MB statistics, and there is the quantum one, which comprises of BE and FT statistics. That has been asked that out of these three statistics, if you say the three types of different gases, which one exerts the least pressure? Which exerts the least pressure? Now, proportion of high energy particles in every distribution is larger than the other two. Proportion of high energy particles in FT statistics is greater than the B and MB. So it would imply that FT or fermion gas, for that matter, it will exert the highest pressure. And whereas proportion of low energy particles is maximum in case of BE, so which implies that it will exert the least pressure. So FT will give the highest pressure and B will give the least pressure. Now the second or the next problem is we need to show that MB distribution is the limiting case of B and every distribution. Is the limiting case of BE or and FT distribution. So if you write B and FT distribution together, so BE and FT can be written as Ni is equal to Gi e to the power alpha e to the power beta Ei plus minus 1, where beta is equal to 1 by kT. And so this is this plus minus 1, this is plus for FT and minus for B. So we have written the two distribution together. Now in this case, if this quantity E alpha by Ei by kT, this suddenly becomes much greater than 1, then we can simply write Ni is equal to Gi divided by to the power alpha power beta epsilon I So this is nothing but your MB distribution. So this practically this means that we have a small number of particles per quantum state. So for small number of particles per quantum state, that means the value Ni by Gi, this becomes much less than 1. If this is greater than 1, this becomes much less than 1. So small number of particles per quantum state, both P and Ft, they convert into MB distribution. And this gas is then called rarefied gas.